this, find AF, we're going to use what we call Stewart's theorem. Stewart's theorem is used if a Savian, because in a triangle, the line that runs from the vertex to one side is called a Savian, divides that side into a given ratio. As you can see, AF divides these sides BC into 5:6, while other two sides are given also. So let's use it, but I will prove the theorem, so let's just solve after I will prove it. So to get AF is equal to the square root, of 6 times 10 squared, that's the 6 you are seeing there, plus 5 times 8 squared over 6 plus 5 minus 6 times 5. So that's what we call Stewart's theorem. So this is now equal to this 600 plus 320, that's 920 over 11 minus 30 on the square root. So this is 920 minus 330 is 590, that's over 11 on the square root. And this should be 59, that's 53 points, that's remainder 7, that's 63. So on the square root. So I think from the option, the best answer is C. That should be 7.3 something. So that's the answer. So let me prove Stewart's theorem. Add an auxiliary line, that's the height of the two triangles, since they have the same vertex P. So I have this. So let me call, okay, as you can see, let's call this point, let's call it X, and this is the height, so this H. And let's call, okay, let me wipe this. This is no more N, because from here to here is N. So I'm saying that from here is now N minus, let's call from here to here X. So this is now N minus X, while the total length is still N. So let's look at triangle. So in triangle PXR, we'll see that Q squared is now equal to H squared plus N minus X all squared. And expanding this, we have that this is N squared minus 2NX plus X squared. Yes. So let's call it equation 1. So, and if you look at the other triangle, the other right angle triangle, which is now PXQ, we'll see that R squared, that's same, this is Pythagorean theorem. By Pythagorean theorem, is now equal to H squared plus M plus X all squared. So if we expand this, we get H squared plus M squared plus 2mx plus X squared. So that's equation 2. So, you know, we introduce H and X, so we need to eliminate that. Looking at the first equation, you see minus M minus 2nx, and we see plus 2mx, so we can't eliminate. So what do? Let's multiply equation 1 by M and multiply equation 2 by N. So I have, which implies that if I multiply the first equation by m, so I have m q squared equals mh squared plus mn squared minus 2mnx plus mx squared. So that's equation 3. That's equation 1 times m. So y equation 2, let's multiply by n. So I have nr squared equals nh squared plus m squared n plus 2mnx plus nx squared. So that's equation 4. That is equation 2 times n. So why did I do this? So that we can eliminate 2mnx. So if you add equation 3 and 4, so adding equations 3 and 4, we see that this is mq squared plus n r squared equals h squared is common, so I have m plus n h squared that we are adding correspondingly. Why this? We have m n squared plus m squared n. This one is 0. Why here we have m plus n all times x squared. So we added correspondingly. So here we can still factor because m plus n is common here. They both have mn. So I can factor mn. First one has n. There is left why this one has m. Plus mnn plus m plus n times x squared. So what do you notice? They both have m plus n. So we'll factor it. I have m plus n. They all have that. So we are left with h squared plus mn plus x squared. Yes. So this is mq squared plus nr squared. So remember, we are looking for, we can replace, as you can see, look at triangle. So if you look at triangle PSU, we see that h squared plus x squared is now PU all squared. So okay, let's continue. We have mq squared plus nr squared equal to m plus n times, so h squared plus x squared is now pu all squared passed by Pythagorean theorem, while we are left with m n here. That's so looking at it, you see that h squared plus x squared is now the hypotenuse, which is pu all squared, which, and that's what we are looking for. Therefore pu all squared, or maybe pu is now the square root of mq squared plus nr squared over m plus n minus mn. So that's what we call Stewart's theorem. That's what I use, as you can see. That's what I use here. So thank you.